Well, welcome to this short nudge video for MOP WM6 in the Waves unit. Rather than focus on only one particular question that you might see in this MOP, I've actually picked a diagram that shows up a couple of times in your questions. And one of the problems with this one is that it's very small on the screen, and so I've done something on my screen that you can't really do very easily on yours, and that's to blow it up. So I will tell you to maybe get a clear straight edge, like a ruler or something like that, and hold it up to your screen to help you reference some of the locations that they ask you about. Because they're going to ask you a couple questions. One is about constructive versus destructive interference, and one is how big the wave would be at the point of interference. So what we're talking about here are two waves that are traveling in the same medium in opposite directions. So here, for example, we might have a rope or a string, and we've got kind of a taller wave that might be moving rightward and a smaller wave moving leftward. They have different amplitudes, they have different frequencies and wavelengths, so the interference pattern can be quite complicated. This is an important characteristic when you're looking at things like why we hear sounds the way that we do, because all the sounds that we hear are actually a mixture of many waves traveling through the air and eventually hitting our ears, and this complicated interference pattern determines what exactly we hear. The same is true of light waves. If we have multiple light waves hitting our eyes at the same time, it's actually the interference pattern that registers what we actually see. So this is just the beginning of seeing what happens when waves interfere. So if we have this snapshot here of the two waves, and it doesn't matter whether they're moving left or right, just they're moving in opposite directions. Suppose we're asked about position C, which I've circled here in purple. And somebody might say, well, first, what is the amplitude of the wave at the point where those two wave patterns interfere? Because the medium that they're traveling through cannot do two things at once. It can't be 2 units tall, like you see on the very short one. I'm going to put a little purple dot there. And it can't also be 3 units tall at the same time. So we use this principle of what we call superposition that describes what happens during interference. And it's actually a very simple kind of property. It's a property known as addition. It just means that the medium will be the sum of the two individual parts as the waves come through. So since we have an amplitude of 2 for the small wave and an amplitude of 3 at the same place on the medium, that would give us an amplitude of 5. So if I were to draw a wave pattern, I would have a point way up there, 5 units up. So we would call that a plus 5 since it's above the reference line or the equilibrium line. Now, because we have both waves in the form of a crest at that location, then we are going to form a bigger crest, and that's what we call constructive interference because we've constructed a bigger wave. Now, if we look at what happens here at D, we have the small wave. Again, we're at the very peak there, so I'll draw that in green. But the bigger wave, we're actually not on the top of a crest there, and so we have a smaller wave amplitude at that particular location. So when we add those particular amplitudes together, it's 1 plus 2 for a total of 3. And because we're still in the above the equilibrium part, we would call that a positive 3 amplitude there. Notice the wave interference resulted in a bigger wave crest, and so we again call it constructive interference. If we look at position F here, kind of randomly pick these, we have the smaller wave. We're at the very bottom of a trough. We call that a negative 2 amplitude. Any trough we just treat as a negative number. And then we have a positive 3 for the amplitude of the bigger wave. So when those two combine, we're going to add a positive 3 and a negative 2, which gives us a positive 1. And notice now what we've resulted in here is a smaller wave than the two individual parts. We've actually combined a crest with a trough, resulting in a smaller amplitude. And that's what we call destructive interference. So you can use the same kind of principle when you just look at any particular location, whatever the two wave amplitudes are that meet at that spot, just add them together, treating crescent trough says opposite signs, and it's just like regular integers being added together. They taught you that sometime in middle school math class, if not before. So hopefully that helps you with the questions where you see this diagram. Kind of move a little closer to the screen and make sure you're looking at the right place on the screen. Maybe put a sharp little point there or something. Don't mess up your screen, and that might help you a little bit. So if you need any more help, of course you know where to find me.